Okay. Today I'm gonna briefly talk about thermonuclear fusion. It's not gonna be a video series that based on what I've been reading on Tokamak by John Wesson. As every video series I have been made related to plasma physics, I always told you that I am a beginner on the plasma physics. Those videos are helping myself to learn plasma physics and fusion reaction. So please forgive me if I make mistake, and I would definitely appreciate it if you can give me some suggestions or some comments on the mistake that I made in the video. So today I'm gonna have a overview. It's pretty much the first few sections on chapter 1 of Tokamak. So nuclear fusion has been around here for several decades. The common reaction they're using, at least when it become a commercial reactor, it will be deuterium plus tritium become helium I think it's kind of awkward. Yeah, that's right. So the Tokamak make the notation kind of weird, and plus one neutron. So you can see that deuterium has one proton, one neutron. Tritium has one proton, two neutron. And helium has two proton, two neutron, and that's one neutron. So if you learn a little bit about high energy physics, then the parity is conserved. So the baryon number is conserved. So you can just simply quick check about the mass of this. So that's PMD T equals MHE, mass of the helium, and mass of the neutron. Then it has extra mass. That mass. Finally, we gotta use the things we've seen all the time, but we never got a chance to use it. The famous Einstein equation, E equals mc squared. So c is the speed of light. So this whole reaction will create quite a bit of energy. It will be. You can calculate it yourself. You can just check the mass of all three and then subtract them, and then you get the delta M. The reaction will create 17.59 mega electron volt. So it's kind of hard to understand in this perspective, but I can give you a more commonly understood way, but it might not be really realistic. I don't know. 1 ounce. If you have 1 ounce of tritium, then you can get 4.4 gigawatt hour of energy. So for this, if you find this is confusing, then 4.4 gigawatt hour is around. You can think about air conditioning air conditioner has 1 kilowatt power. Most of the standard air conditioning is 1 kilowatt ish roughly. So that will power about 4.4 10 to the 6 hours. So 4 million hours of air conditioning. So, or you can think of it can power a medium city, 4.4 million people, 4.4 million houses, which is quite amount. Or you can just think. Let's just see. That's how many days, roughly. So years is roughly 3. So we can power. So 1 ounce of tritium can power one air conditioner for 1,000 years. So that's pretty impressive. And tritium as an isotope of a hydrogen, you can extract them from seawater, which is virtually unlimited. But it's relatively expensive. I heard from one of my colleagues that they didn't use tritium for the fuel. They use deuterium reaction. I don't quite know that reaction, but it will also create some energy. But it will give us almost the same mechanism. It will create helium, but I don't know if helium-3 or helium-4. Anyway, for the time being, I won't talk about that. Let's get to the next. So we conclude on the first point, reaction. We have quite a few energy coming out of our fusion reaction. But what's the requirement? As we know that an atom can be classically thinking. Quantum mechanics can think like this. There's like electron cloud, and the core inside is more probability distributed. And say there's our deuterium atom. There's like proton and neutron. And here is our tritium atom, proton, neutron. And there's electron cloud. The electron cloud, the electron will repel, of course. So you can think of those are two. If you want to fuse those two things together, you can think of like two magnets. It's an analogy like two magnets. It will repel each other, and if you get actually super like close enough, it will just merge to one whole magnet. So you can check on the chapter 1. Chapter 1, figure 1.2.1. We know that. So the potential over distance, that's a distance potential. It will look like this. So if an atom going from outside, it has to overcome this barrier. From classically, you have to go through the whole barrier, like, or quantum mechanically, it will have like Turner effect, but it will still require comparable amount of kinetic energy to overcome this potential barrier. So then what we need is a certain amount of time that those two keep in a certain distance, so that the tunneling, if you have really low temperature, we all know that the kinetic energy the kinetic energy of a random moving particle in an ideal gas is this. K is the Boltzmann constant, T is temperature in Kelvin. So if you have two atoms that is relatively cold, but you can just leave them here for a long time, then it always have probability of going through, but it's just like exponentially. It will go like exponentially into the barrier. So it will, if you get really low temperature, it's virtually impossible to happen. It just takes enormous amount of time, or the probability wise it's just almost impossible. So if you got this part, if you keep them for long enough time, the atom might have a chance to tunnel through the barrier. Then you got fusion happen. So basically what I mean is we need temperature and time, which lead us to the criterion. So the book didn't use this approach to solve that. I just, like, for me, this is my conceptual understanding of the criterion of fusion. But the take of the book is basically using power balance. You can check on the book. It's basically the power of heating. Basically, you need to pump in the heat from outside. So there's heating power, and also the alpha heating. So basically, we remember the reaction. They produce helium. The helium is pretty energetic, so it will collide on other particles, deuterium and tritium. So it will eventually heat up the plasma, and then that's the total. So without the detailed calculation, we can just express it. So sigma is cross-section, mu is the collision frequency, I will assume. N is the density, and epsilon alpha is the energy of alpha particle. V is the velocity of center of mass. Wait. Sorry, that might be the volume, or so that's the total heat density. So for fusion to happen without external heating, we basically require this be less than 0, which means instead of putting energy into it, you can actually extract some heat out of it. So we ended up having we cancel the V canceled out. So we have this. And let's make this more neat. So we have n tau e greater than 12 t over sigma mu epsilon alpha. That's a criterion. So if we have, so for K, the temperature equals to 30 keV, we can plug in all the numbers together. So we have 1.5 10 to the 20 meter density time multiplied by time. So you need them to be close enough and also for a certain amount of time. So that's the basic concept of the fusion. What is happening on the field is relatively interesting. I mean, I've just been here for less than a year. I've been into the field for less than a year, so I may not be the one who can have a really sophisticated answer. But so far I can see that people in the community, I mean, in my group, is trying to use simulations to simulate which mode, which instability is governing is created in different region, or how can we which parameter space is optimal for our, or what type of setting is optimal for certain reactor and certain geometry. So far, our computation power can only do a certain region or not in the velocity space, not instead of real space. That's the next step. You can actually simulate in the real space and optimize the reactor shape. That's why we actually have the stellarator, which is really cool looking, but the topic. The topic is definitely concentrated on how to control the transport. That's a jargon that I at first I was in the field got confused. What transport means? That means you need to take bus from France to either from Paris to either or something. It's more of say here is our Tokamak. That's like see the Tokamak is like a donut. You cut the cross section of donut. That's the cross section. So here is a core. Here is the edge, and sorry. That's if I do it up to the scale. Then here is a core. Here is an edge, and this region is pedestal region. So by the definition of pedestal is basically to say there is a radius. The radius, the temperature by radius is like this. So it's not too accurate. So you can see that in the core, the gradient or the changing of temperature is not as drastic as in pedestal. And the pedestal actually have relatively interesting physics that which we're studying. That's one of the topics we're doing, and also we all know that the particle tend to escape due to the thermodynamic property. It always want to maximize the free energy, so it will tend to diffuse. That's why we need a really strong magnet to confine it. So we need to find several ways to reduce the transport, which transport means basically the heat. The heat transport is basically the heat going out of the core to outside of the device, or the particle transport is basically a particle inside of the device get out of the device. And also, it's not as simple as like, oh, we just confine it and let it sit like that. It's more complicated because it has a tremendous amount of nonlinearity with it. So that's why I kind of feel frustrated that we can actually, for most of the things we cannot calculate analytically. We can only let it to computer because it's so far from, as I talked to the professors and postdocs, that they told me that yeah, you can use a simple geometry and add a little bit tweaks to it to play around, but in the real Tokamak you cannot use those analytical tool. You have to use numerical tool or computers to deal with it. So that's a topic in the theoretical like plasma physics, but I cannot talk too much on the experimental side because I've never been to experimental side. I will definitely add more topics as I become more familiar with this field. But so far, that's all I can say about that.